Welcome everybody to Automated Flight Week 5, and this is the third math video. Now in the previous videos I said I would show the step response to some systems, but we also discussed a system, describing a system not necessarily in its parameters, its mass parameter, spring constant and damping coefficient, but in more general terms with the damping ratio and the natural frequency. And I would like to show you a bit about that. Let me pull up a bit of a description here where we start off with the second order differential equation for our mass spring damper system and take the Laplace transform. Now if we do this in a normal way, we can view our mass spring damper system as an actual system and write out its transfer function. Now I've divided in an early stage by m so that I have a second order polynomial here with a leading coefficient of 1, which makes it a little easier to find the polynomials, the roots of this polynomial. But here we still have a description in terms of the mass and the spring and the damping coefficients. We wanted to use generalized descriptions where we found the damping ratio zeta and the natural frequency omega. Well, the natural frequency is the frequency of the system if there is no damping, where b is equal to 0, and the damping ratio is the fraction of the actual damping b over the critical damping, which in our case is 2 times the square root of mk. Now if we look at our solutions and the different behavior characteristics we saw in engineering, mathematics and modeling, the discriminant of our second order polynomial, so if we use the ABC formula, which is equal to b squared minus 4mk, the value of this discriminant determines the behavior of the system. So if it is positive, we know that we have 2 real roots, and we'll have an overdamped system where the solution will be the combination of 2 exponential functions. If the discriminant is equal to 0, we'll have a single root, and the system will be critically damped, and we get a combination of exponentials, but there's an extra t added here. If it is if the discriminant is negative, we know that we get complex roots, so we'll get a combination of an exponential and 2 sinusoidal functions, a cosine and a sine function. But in the specific case where we have no damping, we see we get a purely sinusoidal and output, the combination of a cosine and a sine, where there is no decay. So the oscillations don't increase, they don't decay, they just stay constant. Now if we look at the same table in terms of zeta and omega n, we see that instead of the discriminant we have ranges for zeta. So overdamped where zeta is larger than 1, critically damped where it is equal to 1, underdamped between 0 and 1, and undamped for zeta is 0. And that makes sense, because if b is 0, zeta is 0 as well. And we see the roots of our second order polynomial here in the denominator. There will be purely imaginary roots where we know that this will yield harmonic behavior, so oscillations that just stay constant. Now we can simulate this, and the software I'm using to simulate this is MATLAB, but you can also simulate this with XCOS from Scilab. And let's have a look. I have a figure window here, and I will provide plots for the different damping ratios one by one. We could also, well, I'll give you the first plot, and here we see harmonic behavior, and we also see that it is undamped. There's no increase or decrease in its amplitude. I could also show you different values for the natural frequency, and what we would see for a high frequency we would see faster oscillations, and for lower frequency we would see slower oscillations. So now let's see what happens if we add a bit of damping. So here the damping ratio is 0, we increase it to 0.25, and we see that there are oscillations, but they slowly dampen out. add a little more, and we see that again there are still oscillations, but they dampen out quicker. We also see that the rise time becomes slower. So the time where it reaches approximately 80% of our set point value. A bit more damping, zeta is 0.75. We still see a bit of oscillations, but hardly. And when we go to zeta as 1, we enter the critically damped state, where we see that there are no more oscillations, and the response goes up to our set value. If we add more damping, what we'll see is that it has a similar behavior, but the behavior is a bit slower. Now, if we plot all of these together, let's plot these all together, and then we can see the different behaviors side by side. So we have our undamped in blue all the way past our critically damped in a sort of a green, and our overdamped in a light blue. So here we have a second order system, a mass spring damper system, where we have the step function input, and we see for the different values of zeta what its response is. And this is the end of the video.